In this video we're going to talk about sums and intersections of subspaces. But before I do that, I set you a problem at the end of our last video, which was about a certain subset of the space of all 2x2 matrices with complex entries. So that subset was called U, and it was the subset of all 2x2 complex matrices whose square was equal to the zero matrix. What I asked you to do was to try and work out why that is not a subspace of the space of 2x2 complex matrices. You'll remember that the definition of subspace has three parts. The first part is that it must contain the zero matrix. Well, the zero matrix does have square equal to the zero matrix, so it passes the first part of the definition of subspace. The second part was closure under addition. I'm going to skip over that and come back to it. And the last part of the definition of subspace was closure under scalar multiplication. Well, U is closed under scalar multiplication because if you have a complex number, let's say A in C, and if you have a matrix A in U, then if you look at little a times big A squared, you know from the normal rules of matrix multiplication, that's a squared times a squared. Now A was a matrix in U, so its square is the zero matrix. So that's a squared times the zero matrix, which is the zero matrix. Okay, that tells us that A times big A really is an element of U again. That means that U is closed under scalar multiplication, but it is not closed under addition. That's the reason it's not a subspace. It fails condition 2 for being a subspace. So if we take, for example, let's give this a name, A is going to be 0, 1, 0, 0, you can check that's an element of U. And B will be 0, 0, 1, 0. Again, you can check by squaring B that it's an element of U. But if you look at A plus B, that's the matrix 0, 1, 1, 0, and that is not in U. This means that U is not closed under addition, and therefore it is not a subspace. Okay, let's move on to the topic of this video, which is about intersections and sums of subspaces. We're going to prove two useful results which tell you how to make a new subspace out of two old subspaces. I've written the definition of subspace at the bottom of the screen there for you, just to remind you. And what our proposition on this slide says is that if you have two subspaces, x and y, of a vector space V, then their intersection, x intersect y, is also a subspace of V. So remember that we use this notation with a less than or equal to mean that something is a subspace. So let's prove this. Now, proof that something is a subspace is easy because all you have to do is to check the three conditions of the definition of subspace. So we're simply going to do it for these two subspaces x and y. So first of all, we have to check that x intersect y contains the zero vector. So let's observe that the zero vector is an element of x, and the zero vector is an element of y because those two things are both subspaces, so they must contain the zero vector. So if the zero vector is in x and the zero vector is in y, then it is in their intersection. Alright, that means that condition 1 is true in the definition of subspace. Condition 2, we have to show that x intersect y is closed under addition. So I have to pick two elements of x intersect y and show that their sum is in x intersect y again. So let us let vector A be in x intersect y, and vector B be in x intersect y. Okay, what can we say about A plus B? Well, we know, for example, A and B, they're both elements of X. If they're in X intersect Y, then they're certainly in X. So, because X is a subspace, it's closed under addition. And that means A plus B is in X again. Okay, but the exact same argument shows that A plus B is in Y. A is an element of Y, B is an element of Y. Y is a subspace, so it's closed under addition, so A plus B should be in Y as well. Now we know that A plus B is in X, A plus B is in Y, so A plus B is in X intersect Y. Right, we took two arbitrary elements of X intersect Y, we've proved that their sum is in X intersect Y. That means X intersect Y is closed under addition, and condition 2 for being a subspace is true. Finally, we have to show that X intersect Y is closed under scalar multiplication. So let's pick a vector A in X intersect Y. And we also have to pick a scalar. So let's say V was a vector space over the field which we'll call F. So that means the scalars you're allowed to multiply by come from this field F, whatever it is, real numbers, complex numbers, whatever. Okay, so A is going to be a vector in X intersect Y, and we'll take a number, let's say L in F. Okay, if A is in X intersect Y, then for sure it's in X as well. A is in X, and X is a subspace. We're assuming this, we know this. So L times A is in X as X is a subspace, so it's closed under scalar multiplication. Alright, but the same argument again tells us that L times A is an element of Y. And once more, L times A, we've shown it's in X, we've shown it's in Y, so LA is in X intersect Y. We took any element of X intersect Y, and we took any scalar, any element of the field L, and we proved that L times A is in X intersect Y again. That means X intersect Y is closed under scalar multiplication, so it meets all three parts of the definition of being a subspace, and therefore it is a subspace. Alright, let's now just look very quickly at an example of the intersection of two subspaces. So here is my small example here. We will work with the vector space R cubed, and we'll let U be the subspace, consisting of all things of the form A, B, 0 for A and B in R, which you can check is a subspace of the vector space R cubed. And I will now let V be the vector space consisting of all things of the form 0, A, B, like this, where A and B are in R. And again, you can check this as a subspace of R cubed. And the thing we've just proved tells us that U intersect V must also be a subspace of R cubed, and if you work it out, U intersect V is actually going to be the set of all vectors 0, A, 0, where A is in R. That, by our proposition on this slide, is a subspace of R cubed. Okay, on our next slide we'll prove a similar result, but this result is about a new construction, which is the sum of two subspaces. So if x and y are subspaces of the vector space V, then we have not yet defined what x plus y means. So here is the definition. X plus y is defined to be the set of all things which you can get by adding an element of x to an element of y. So the obvious definition, really, that's what x plus y ought to mean. And what we're going to prove is that that is, in fact, a subspace of the vector space V. So again, what we have to do to check that is to check the three conditions for being a subspace, which again I have copied at the bottom of here. So let's take, first of all, we have to show that x plus y contains the zero vector. Well, x is a subspace of V, so it must contain the zero vector. Y is a subspace of V, so y must contain the zero vector. So remember, the definition of x plus y is the set of all things which you can get by adding an element of x to an element of y. So 0v plus 0v, which by the way is equal to 0v again by one of the vector space axioms, is in x plus y. Alright, so we have shown that x plus y contains the zero vector. It meets the first condition to be a subspace. Condition 2 is closure under addition. So this time let's take two elements of x plus y and prove that their sum is in x plus y. So let's say a plus b and c plus d. Those are going to be our two elements of x plus y. That's what a typical element of x plus y looks like, the sum of something in x and something in y. So here, a and c will be elements of x, and b and d are elements of y. I have to prove that the sum of a plus b and c plus d is also in x plus y. Well, to do that, let's just rearrange this sum a little bit. Remember that vector addition in a vector space is always associative. Again, that's one of the vector space axioms, which means you can re-bracket this any way you like. So a plus b plus c plus d is equal to, just by re-bracketing this using associativity and commutativity of vector addition, you can get that this is equal to a plus c plus b plus d. Let's write down the reason this was true. So this is because vector addition is associative, which means you can re-bracket it however you like, and commutative. Okay, now what can we say about this thing here? A and C, you'll remember, were elements of X. X is a subspace, so it's closed under addition. So this is in X because X is a subspace, therefore closed under addition. Similarly, B and D were elements of Y. So B plus D will be in Y, as Y is a subspace and therefore closed under addition. So what we have is the sum of an element of X, namely A plus C, and an element of Y, namely B plus D, and that is therefore an element of X plus Y, because it's something in X plus something in Y. Okay, we took an arbitrary element of x plus y, we added it to another arbitrary element of x plus y. We've shown that the result is still in x plus y. So x plus y is closed under addition. We have just the final condition to check. Number 3. Closure under scalar multiplication. So we let a plus b be in x plus y, where a is in x and b is in y. I know I can write every element of capital X plus capital Y that way. And we need a name for the field over which V is a vector space. So let's say this vector space V was a vector space over the field F. That means you're allowed to multiply, the scalars you're allowed to multiply by come from the field F. Maybe F is the complex numbers, the real numbers. Maybe it's the finite field with 5 elements, whatever. But in any case, in order to show that x plus y is closed under scalar multiplication, I have to pick an element of x plus y and an element of that field. So as usual, let's call it L. Then what I have to do in this final step is to show that L times A plus B is an element of x plus y. Okay, to do that we use the vector space axioms. One of the vector space axioms said that there was a distributivity property, that you could multiply out brackets like this. So L times A plus B well, that's equal to LA plus LB by the vector space axioms, by one of the vector space axioms. Now, L times A is in X, because X, being a subspace, is closed under scalar multiplication. Similarly, Y is a subspace, so it's closed under scalar multiplication. So L times B is in Y. So L times A plus B, we've just written it as an element of X plus an element of Y, and therefore it's in X plus Y. Oops, wrong tool. Is in X plus Y. Okay, we have now shown that X plus Y is closed under scalar multiplication, and therefore we checked all 3 of the subspace properties for X plus Y, and we verified that it is a subspace, and our proof is done.